Okay, welcome back everyone to our new year and a new start on our AI robotics seminar series. Today we are having our first speaker of this year, Mojtaba Sharifi. And Mojtaba is an assistant professor at California State University. He just recently started, and before joining California State University, he was a research fellow at the University of Alberta, in particular at the Department of Electrical and Computer Engineering and the Department of Medicine. Mojtaba is interested in intelligent control, dynamics, and design of robots used in biomedical applications such as rehabilitation, surgery, and imaging, autonomous human-robot interaction using impedance control and learning, wearable and assistive robotics such as exoskeletons, prosthesis, and orthosis, haptics, collaborative robotics, and telerobotics. Mojtaba published more than 50 scientific articles and chapters in well-respected scientific journals, conferences, and books. And he will be the first organizer of a workshop on intelligence control methods and machine learning algorithms for human-robot interaction and assistive robotics. Mojtaba, that sounds super interesting. I hope you will tell a few words about this as well. But the main topic of today's talk is autonomous locomotion, trajectory shaping, and nonlinear control for lower limb exoskeletons. Mojtaba, thanks again for being here with us. Your talk sounds super interesting, and you have a very interesting background, and we look forward to hearing you speak.
Thank you, Igor, for the introduction. I'm going today to present about one of my research topics, which is on autonomous locomotion, trajectory shaping, and nonlinear control for lower limb exoskeletons. So that was the work that I did in my previous position at the University of Alberta, as Igor mentioned, in the electrical and computer engineering department and also medicine department, which was supported by a smart network, which is a network of different faculties at the University of Alberta. Okay, let's just start with this question that why human-robot interaction and collaborative or assistive robotics are important and why we need to do research on the control of these systems. Well, that's because of having human as the very important part of this system and the concerns that we have regarding the human safety and comfort. Basically, in these systems, the human is the recipient of the physical assistance provided by the robot, or he or she is doing a collaborative task together with the robot. So we want to enhance the quality of life for the human, and we want to make those physical tasks simpler or easier using these autonomous systems. So in these videos, you can see an operator that is doing a collaborative task with an industrial robot. And you can see this surgical robot that is doing a suturing task based on the motion of the surgeon's hand. And you can see upper limb and lower limb exoskeletons here. So that's the upper limb robot by Harmonic Laboratory, a company in the US, and this is the robotic lower limb exoskeletons. So at the same time, the existence of human in these HRI systems, human-robot interaction systems, can raise some concerns due to their unpredictable behavior of the human, having non-passive interaction between the robot and human, and also requirement of identifying the intention of the human operator. So for the control of these robotic systems, we need to consider human in the loop of the controller. So this brings some technical challenges regarding the robot stability and the human safety, and also the shared autonomy or authority between the robot and human. So in my research for over the past 11 years, I have made effort to resolve these challenges, and I had a general goal to balance major HRI concerns. And the first concern is the human authority and the robot autonomy. The second I would say, concern or characterization. Like we can look at it from different points of view. But the second one is the system stability and the human safety. And the third one is the task performance. So I try to offer trade-offs between these three concerns from different points of view in the field of control, learning, and design. So most of my research was on the control. Recently, I moved to learning, and I have some projects on the design of these robotic systems. So in this presentation, I will just talk about my second research area, which is on interaction learning and autonomy for assistive exoskeletons that I started from the end of my PhD and also in my post. So as you may know, exoskeletons are being used in two applications. The first one is for empowerment of able-bodied people and workers in their hazardous or heavy manual tasks. So basically, we want to prevent from their injuries. But the second application of these exoskeletons would be for assistance and rehabilitation of individuals with disabilities, basically after having injury or having disability. However, doing research in this area is challenging due to having a continuum of interaction between human and robots and the lack of measurement for interaction forces or torques compared to other HRI systems where we have one or 2 points of interaction. So instead of that, we have a continuum of interaction, and that makes it hard to measure the interaction forces. So now the question is, what are the basic requirements for controlling these systems? Well, the first one would be estimating the user effort and identifying their interaction. So we need to somehow estimate that kind of interaction, which is hard, as I said, to measure. After that, the second challenge or question would be path planning for these exoskeletons, how we can do motion planning and make it personalized for each user. So in this project, we propose a control strategy with 2 levels of autonomy. At the high level, we propose an intelligent locomotion trajectory shaping to make it personalized for each user. And at the low level, we have a torque estimator and controller to estimate the torque and at the same time control the exoskeleton to track the generated trajectory at the high level. So to design the control strategy, we can formulate the nonlinear dynamics of the human exoskeleton system in this form. So the first term represents the inertia. The second term represents the Coriolis and centrifugal and damping elements of the robot dynamics. I would say robot and human both together. And the third term is the gravity vectors. On the right side, we have torque of the actuators of the exoskeleton, and also the torque of the human wearer, like the torque that the human can generate by activating, his muscles, by contracting muscles. So we have these dynamics, and this dynamic has some properties, such as having positive definite inertia matrix, which has a lower band and an upper band. Also, it has linear parametrization characteristics, such that we can basically put all of the variables on the left side in a matrix and all of the parameters in a vector. So we call it linear parametrization. So in our strategy, we have 2 components to generate the personalized gait trajectories to be tracked by a position controller. The first component is central pattern generator, which we call it CPG. CPG, and we made that CPG adaptable to human-robot interaction, as I said. But generally, CPGs are a set of connected networks that they can produce coordinated patterns or synchronized patterns for a rhythmic activity such as walking. So they are good mathematical tools to generate those synchronized and rhythmic motions for different joints of the human body during walking. The second component in our control strategy is an adaptive disturbance observer for online estimation of the human-robot interaction torque. So,
Michelle, may I ask a question?
Go ahead.
You write on the first point that it's based on non-oscillatory inputs. What is the relevance of this? And also for walking, is most of it like, wouldn't most of it be considered oscillatory, or what is the motivation?
Yeah, basically, you know, with CPG, you can make sure your response is time continuous and rhythmic, but the input to that dynamics, the input can be discrete time and can be non-oscillatory, you know? So you can disturb the response with a non-oscillatory input, even though the output would be oscillatory and still time continuous. So yeah, for example, you decide to change like the phase difference between adjacent joints, like between the right hip or left hip. So you can do that with a kind of discrete input. But they are still synchronized. They are still, you know, moving without any delay or stop.
Okay, cool. Thanks.
No worries. So the second component, as I said, is a kind of torque estimator. As I said, usually we don't have force sensors on the body of the exoskeleton. So we developed an adaptive disturbance observer. So we could use also EMG signals, but the EMG would suffer from calibration inaccuracy, muscle fatigue, electrode positioning, and muscle skin conductivity variation. And also it is not that comfortable for the wearer to have a lot of EMG electrodes on the body. But in a lot of research at the end, I would show that we use EMG for upper limb exoskeletons. But generally, it's challenging to use those ones. So because of these challenges, we decided to have a nonlinear disturbance observer to estimate the human interaction torque. So here we can see a schematic diagram of this two-level control strategy. So we have some Fourier series to mathematically formulate the primary experimental data and generate time continuous trajectory as the initial trajectory of motion. And this trajectory would be reshaped or updated by the adaptive CPGs in terms of the estimated human torque. And the output of this CPG will be tracked by this nonlinear controller and will be implemented on the exoskeletons. So at the same time, as I said, we have an adaptive disturbance observer that has some feedback from the exoskeleton that can estimate the human interaction torque. And based on that, we can estimate the human energy, like the energy that is transferred between the exoskeleton and the human. And basically this energy would change the generated trajectory by the CPG. So when we estimate the human-robot interaction torque, we would pass it first through a dead zone function to take care of more meaningful torques with enough large magnitudes. Basically, if the torque is higher than, a positive or lower than a negative threshold, then we would consider it as a meaningful torque between the human and robot. And then we use this estimated torque in this formula to estimate the energy. So we have torque multiplied by velocity, and that would be a kind of magnitude for the power that is transferred between the human and exoskeleton. And then the time integral of that would be the energy that is transferred between them. So Here is the mathematical formulation of CPGs that I was talking about. And this is somehow our high-level controller. So in this dynamics, we can generate and change the frequency of the motion, the amplitude of the motion, and the phase of the motion for each joint. And yet, as you can see, these are second-order differential equations. And we added these terms, which is the summation of all of the energy components transferred by all of the joints, including hip, knee, and ankle for different exoskeletons. And then by transferring energy, we can change the frequency of the motion and amplitude for the whole motion of all of the joints. And also, by having this frequency and amplitude, we would substitute these values into the Fourier series that we have and generate time continuous and rhythmic motion by this one. Also, this frequency would go to the dynamics of the phase for each joint, and the difference of the energy between adjacent joints would generate also a phase lead or phase lag between two joints that are close to each other. So somehow we would take care of all of the energy between the human and exoskeleton. If the person wants to accelerate, he would generate some positive energies to increase the frequency and amplitude at the same time, because when we want to walk faster, we would increase the frequency and amplitude both together. Or when we want to walk slower, we would decrease the step size, we would decrease the speed of motion both together. But in addition to this, increase or decrease in the rate of walking, we also sometimes we want to change the synchronization between joints, like between right hip and left hip, between, for example, right hip and right knee. So we are walking with different kind of patterns between different, humans. So we can also change that kind of phase difference. So at the low level, we designed a nonlinear position controller in terms of the tracking error. We can see the terms of the human exoskeleton dynamics, like such as inertia, Coriolis. And in this nonlinear controller, we designed that to be in terms of the tracking error. And with that kind of design, we could prove the stability using Lyapunov functions. But in this structure, we are also estimating the human interaction torque. As you can see, the hat sign, this shows that we are having estimation here. So for this estimation, we use a nonlinear disturbance observer in terms of the nonlinear dynamics again. And this specific disturbance observer would have some intermediate variables to estimate the human-robot interaction. And with this dynamic, with two levels of estimation, we can somehow filter noises and everything that we have in the signals and make a kind of time continuous estimation for the human torque. So I think you can follow the paper that is going to be published in Adaptability semi-transactional mechatronics, but we had a couple of steps to prove the stability using this control law and this kind of two-level disturbance observer. But at the end, we would get the estimation of the human torque, and we will put it here to close the loop of the controller with having the interaction between the human and exoskeleton. At the same time, this interaction will be used here in this energy that we are using for CPG. So the human interaction torque estimation will be used in both CPG and also the controller at the low level. So here is the Lyapunov function that we use in terms of tracking error and also the estimation error for the human torque. And at the end, we we proved that the error of tracking and the error of estimation will converge to a compact zone, to a bounded region. And this bounded zone would be in terms of different errors that we have, on the dynamics of the human exoskeletons. But at the end, we would prove that bounded stability or bounded convergence, I would say. So now I'm going to show the experimental results. So we fit an 8-term Fourier series to formulate typical trajectory of walking. So, and you can see the coefficients of these Fourier series here in this table. The first wearer I'm going to present the result for 2 wearers. The first wearer applied torques at the beginning of the walking over the first 4 steps. As you can see, is changing the amplitude. And as you can see, the rhythm of motion is also changed the frequency of walking. At the beginning, it was slower. You can see the time period is bigger. And from this point, you can see the time period is smaller. And he could change the gait amplitude by 15% in this experiment based on the dynamics of the CPG that I presented. And here you can see the performance of the tracking controllers. You can see that the error of tracking for right knee and hip converges to a bounded region or compact zone, which is smaller than 2 degrees. And this is acceptable to have a kind of tracking for the trajectory of walking. And here we can see the major torques that the person applied on different joints of the exoskeleton. That's me as the first wearer. And as you can see, I applied most of my torque on my right hip. So, and very small torques on the other joints like left hip or knee joints. So that was my preference, but everybody is different during our experiments. We saw different behaviors from different wearers. So I injected most of my energy through the right hip, as I mentioned, and the effect of this variation can be seen here on the frequency of walking. So I increased the frequency of walking by 42% from around 1.2 radian per second to 1.66 radian per second. And as I said, because most of my torque was on the right hip, you can see the energy, most of the energy is transferred through the right hip compared to other joints that have very small values. But you can see here that I just have some decelerations using my left knee. So basically I use my left knee to decelerate and control the speed, and I use my right hip to accelerate the motion. So that was just for me. But here you can see the result for the second wearer. So second wearer applied major torques over the first 6 steps to adjust the speed and the amplitude of the motion. And the maximum torque was less than 3.75 Newton meters. And as you can see, transferred most of the energy through the left hip, as you can see here. The green one, dash green, is the left hip. And after that, using right hip. So use both left and right hips to accelerate the motion. And as you can see, the frequency got changed over 6 steps. And after that, he didn't apply kind of major torque to change the speed because he was fine with that kind of synchronization. So the speed and the amplitude didn't change after this time, after 20 seconds and after 6 steps. So to understand the synchronization, we also plotted the right and hip trajectories with respect to each other. So the motion is rhythmic, so we are repeating the same trajectory over the steps. But as you can see, for the first wearer, we have an average phase lead of 13 degrees for the right hip motion compared to the left hip. But for the second wearer, we have a phase lag of around 4.8 degrees for the right hip compared to the left hip. And as you can see, we started from the dashed red trajectory and moved to the black one. So as you can see, the deviation of the trajectory for for the first wearer and the second wearer is completely different. And to understand the phase lead, you have to just consider one point here on the red trajectory and get the corresponding point on the final black trajectory. And then you can see if you get the point again on the red one, you have a kind of phase lead for the right hip. But for this one, if you get this point on the red trajectory and get the corresponding point here, and then get the corresponding point on the right hip, you can see we have a lag in this motion because the motion is toward up, and then we went toward down on the black one. So somehow, compared to initial trajectory, we have a phase lag for the right hip and phase lead for the right hip for the first wearer. Here is the video of those experiments for both operators and wearers. So that's a long video. So we had it for more than 100 seconds for each wearer. That's for the first wearer. And that's personalized, which means that the user can change the amplitude of the motion. As the height of the user is bigger, or when they are taller, they can, increase that amplitude to be suitable for themselves. Even though these exoskeletons in the market, they have a predefined trajectory. So we cannot change somehow, the synchronization between the joints, or the amplitude that much. There are specific levels that you can choose, but using this intelligent controller, you are able to change it over the first couple of steps, and then you can walk with the same pattern for the rest of your walking. So that's for the first wearer, and there is another part for the second wearer.
You're showing this, maybe a question. You were speaking at the end of, walking in the same pattern. How good or how fast do they usually adapt to pattern changes?
It depends on the parameters that you change. You basically adjusted in the CPG dynamics. Mm-hmm. So we made it very fast. Like I would come back to the results. Like the person applied a torque, on just one step. And during one step, we have the complete response. Like the response of CPG is faster than one step. So in that case, if you want to accelerate, you can do that just in one step. And then if you want to do that over a couple of steps, you can do that step by step to get your, desired trajectory. So the response of CPG is pretty fast. And that's based on the parameters that you select for the CPG dynamics. So that was a kind of trial and error to get the best, parameters there for that dynamics. And we did that just by doing different experiments. When you see that, it's not enough fast, then you need to work with that, make it better. When there is sometimes there is an overshoot, again, you need to make the parameter selection better. But you know, typically it's hard to walk with these exoskeletons. You wouldn't walk like a normal locomotion. So it's really hard to make it comfortable and natural for each user. But we try to do that without using our controller. And we have a research-based package for this exoskeleton. So we are able to change everything for this exoskeleton, because this is mostly for the clinical settings, and they are not able to change anything, because you can just use the app, mobile app for that. So that was the end of this presentation, but I want to talk about my other projects and other studies that we have in this area. So in addition to this research, we also started new collaboration with researchers in the field of natural language processing, NLU, to integrate auditory data via speech processing in locomotion planning. So we could combine physical HRI with social HRI, such that the robot or exoskeleton, this is the last experiment that I did in Canada before leaving, and I and other students wore the exoskeletons, and we are talking to exoskeleton using the microphone, wireless microphone that we have. So we can command the exoskeleton based on our vocal data, instead of having the app of these exoskeletons and using their buttons, which is really hard because the person needs to have a kind of support in getting that by a walker or a cane. And at the same time, it's hard to hold that mobile app. So we use speech processing here to get the vocal data in a noisy environment and recognize the user among other people in the environment. So also my third research focus is on the development of soft and wearable robotic systems. So in this project, we basically designed and fabricated kind of like light and soft exoskeletons. So we have soft actuators, as you can see, artificial muscles, to actuate the shoulder and elbow joints. And that was a result of a proposal that I wrote for my postdoctoral research. And we developed 3 generations of this exoskeleton, and this is the first generation. But we made it lighter and more effective in the next project. As you can see here, this is the first version. This is the second version of the exoskeleton. But we also integrated biological signals such as EMG. We can see we are using EMG signals for the shoulder and elbow muscles. And based on that, we are commanding the exoskeleton to assist the person, for example, here for weight handling. And here I'm not attaching the exoskeleton to myself to show how my muscles contraction can command this exoskeleton to move. So we have EMG electrodes on the shoulder muscles for abduction, adduction, and flexion extension, and also for elbow flexion extension on the biceps muscle. So as Igor mentioned, we are going to organize an interesting workshop in IEEE ICRA conference this year, which is on intelligent control methods and machine learning algorithms for human-robot interaction and assistive robotics. So I try to invite the best researchers in the field of human-robot interaction and assistive robotics. So we have people from MIT, Imperial College, University of Toronto, TU Delft, and also other universities in this conference. And I would invite you to send your short papers. We would accept abstracts in this workshop. And this is completely separate from the submission that people had for the main conference, ICRA. It would be nice if you have any results for your research, you can send it to that workshop, and we would present some selected papers. We would select some papers to just basically have presentation at the end of this workshop, and their videos or their abstract will be published on the website of that workshop. So I think, Igor, maybe you can have a talk there if you want, but we have some people from University of Toronto. At that time, we didn't talk about it, but we have Professor Nejat and also another faculty member of University of Toronto in that workshop. But yeah, that was my presentation. Thank you for your attention.
Mojtaba, thanks so much for your super interesting presentation. To me, this is a very exciting topic. I have not worked in this space much. So I have, additionally to some of the technical questions I had earlier, I also have a few high-level questions for you. So first of all, what do you see like as the big goalpost for exoskeletons? Because as I understand it, as you mentioned in your talk, there are some currently available on the market. What is, like, from the user experience perspective, their main limitation?
You mean what's the goal of using those exoskeletons? Or
no, I mean, what is the big, besides improving like control, what do you see as like the big research problem or the big obstacle to solve for widespread use?
Yeah, we have a couple of issues, I think, for the available exoskeletons in the market. Regarding their structure, most of them are pretty heavy. And that makes it really hard to use it even for able-bodied people. Because when you use it and the exoskeleton is pretty heavy for lower limb, you have to hold it with your upper limb muscles. So sometimes you would feel pain even after using the exoskeleton for 30 minutes. So you are adding around, for example, 20 kilograms to your lower limb, and that makes it hard. So also, if something happened, again, the chance of injury is higher. So as you saw in those videos, even with the Reebok or Indigo exoskeletons in clinics, there are a couple of people around the person to support that person, to take care of that, So we have some safety concerns still because of, the heaviness of that exoskeleton. For the control, I would say there was some issues because of having repetitive trajectories that, we try to address that issue in our research work. There are some other papers as well in this area that was published recently. So also they tried to make it personalized. So personalized motion was another issue. Also, in addition to have a trajectory, we are integrating postural stability components. Like sometimes you can generate the trajectory and make it personalized, make it fast or slow. But for some people with disabilities, you want to provide the postural stability as well. Like if they are falling down, you need to change the trajectories, rapidly. So this kind of, adding postural stability elements to the motion generation element, that's another area that we also work on that using new PhD students. So one of them is focusing on DCM, which is a method to adjust the postural stability together with CPG that I presented today. So that's another thing. Also, we can use reinforcement learning. So we use reinforcement learning in this project. As you can see here, we are getting EMG data from each user, but the pattern of EMG for each user is different. So we are using reinforcement learning and having some reward function in terms of EMG and in terms of the motion to get the best adjustment for the parameters that we have to generate the motion. It's somehow, for example, if you imagine CPG that we have, we can adjust the parameters for each user using reinforcement learning. during the task. So that's another contribution that we can have, and that would be kind of like a kind of, how to say, kind of combination between computational AI and analytical AI. Like the controller is still analytical, like we have a classic controller, but the parameters of that controller will be selected by machine learning algorithms.
Okay, thanks.